Hello to all. We're waiting for everybody to come in the room before we start, so we'll start in a minute or so. Those who have just joined us, we'll start in a few seconds. So, hello to all. I am Normand Mousseau, Scientific Director of the Trottier Energy Institute. I would like to welcome you to this presentation of the second report of our Canadian Energy Outlook, a third edition already, Pathways for a Net Zero Canada. In this presentation, we'll present you the model, the main scenarios that are considered. We'll also, of course, highlight the main results and a few key takeaway that will before we let you ask a question. So you can immediately start filling a question at the bottom in the box, and then we'll entertain these questions at the end. So today I will be presenting. Leading the beginning of this presentation. We'll also have Olivier Ban, who will be presenting the Pole E3C, and Kathleen Vaillancourt, CEO of ESMIA Consultant, who will be presenting ESMIA. And then the main elocution will be done by Simon Langlois-Bertrand, who is the lead author and researcher at the Institut de l'Énergie Trottier, and Louis Baumier will be leading the questions. So a few words about the Institut de l'Énergie Trottier. The Institute was created in 2013 with a grant, a gift from the Trottier Family Foundation. The support was renewed in 2023 until 2030. So this allows us to pursue our mission, which is to support the training of engineers and scientists with the idea of understanding the energy transition. We also supporting research project linked to these questions. And finally, a big part of our work is to work with government and work at dissemination of knowledge and thinking about how we can operationalize this transition, and what the seminar and the Energy Outlook are part of this effort. We also have a number of other projects, including evaluation grid for the biomass in the context of net zero, reducing the electricity peak demand, how we can think about that. And we're co-leading with ISVIC and the University of Calgary, the Energy Modeling Hub. So let me now move to the other partners for this Energy Outlook, ESMIA, with Kathleen Vaillancourt.
Hello, so ESMIA is a modeling and consulting firm based in Canada, in Montreal, since we are around for more than 10 years. So we do provide a bunch of services around what we call 3E system modeling, so 3 for energy, economy, environment, for strategic decision making. So we are working with a bunch of government consulting firm, private companies in North America mainly, but also globally. We have a large teams of modelers with very strong background in engineering, mathematics, economic and climate change sciences, and some of us have more than 20 years of experience in modeling activities. In terms of service, we provide 3 types of service. So we do develop model from scratch for clients worldwide. So we work in Europe and Asia as well. We do provide training and support for those clients who would like to develop their own model. And finally, as this project, for example, we do apply our proprietary model for the analysis of complex problems like energy transition would be the main topic we are studying these days, but we also do other types of studies. So we have you have on the right different our modeling suite. So for this project, the NATEM model was used, but we also now have our NATEM power model for hourly look at the electricity system, rate vision model, which study the impact on rate and electricity bills, and our macroeconomic impact NAGEM. So thank you for being here.
Thank you, Kathleen, and Olivier Ban, who is also who's been with the Pole E3C, who has been also with the energy outlook and supporting the energy outlook since the beginning.
Thank you, Armand, and hello, everyone. I'm Olivier Ban, professor at HC Montreal and co-director of the E3C Hub. So the E3C Hub is a multidisciplinary hub at HC Montreal with 13 professors from several departments, a research professional, and a coordinator. Our mission is to advance the transition towards a sustainable society and economy in partnership with various organizations such as the Institut d'Énergie Trottier. To this end, we are developing 3 models, in particular the UDMERGE model, a global integrated assessment model, so similar to the models used by the IPCC. UDMERGE can be used to analyze climate policies involving both mitigation and adaptation strategies. However, this model does not offer the same level of detail for the Canadian energy sector as the model developed by ESMIA, which were used for this energy outlook. As part of its mission, the E3C Hub is also involved in knowledge transfer activities. So we are therefore pleased to be taking part in this 3rd edition of the Canadian Energy Outlook, just as we did for the 1st and 2nd editions. So I now give the floor to Simon for the main presentation. Thank you.
Thank you all. Good afternoon, good morning, depending on where you are. Very happy to present to you the results from this 2nd report. First, as most of you well know, this is part of a much broader set of efforts from different organizations over the past few years to try to clarify and get some answers as to what is needed and required by trajectories to meet the net zero target by 2050, including by ECCC, the Canadian Climate Institute, the CER, and many others. For us, it's the 3rd edition, so especially similar to the 2nd one, which was also net zero in 2021. And this time around, we took some cues from the hundreds of pages of the report from the 2nd edition. And instead of releasing just one report, this is a year-long project that we've broken down to make it much more digestible, of course, but also to present the issues from different angles. So we had a report number 1 coming out in January, presenting the current state of energy and GHG sources in Canada, recent trends, and so on. So this is report number 2, which includes the main modeling for net zero scenarios. Just to mention as well that the reports will be available on the IT webpage tomorrow, and then next week at some point we'll also publish or make online, put online, sorry, platform to explore the results in more detail with some summary of analyses that you can find in the report in lengthier form. So after that, the rest of the year will be spent on a series of report and projects that delve into strategic challenges or key themes that come out of these modeling results, as I'm sure we'll get into in the question period and in part of the presentation. So as Olivier and Kathleen mentioned before, so in the Canadian Energy Outlook, we use NATEM, and among its main strength is the very rich detail for technologies, with over 4,500 technologies included in a full representation of the energy system. We also get results at the provincial level, which are discussed in the report. Of course, you have to keep in mind that this is still a national optimization for the meeting of the different constraints and hypotheses. But nonetheless, there's some discussion provided there as well. So net zero is not meant province by province. in other words, but just at the national level. There's also full coverage of emissions, which, with the exception of LULUCF, where there's partial coverage. So we do have in the application of the NATEM model here, coverage of fugitive emissions, non-energy emissions like industrial processes, agriculture, and so on. And part of LULUCF is captured through the integration of some biomass-related or bioenergy-related technologies, as I'll get into in a little bit. So just to show you the main scenarios, we kept it very straightforward. So there's a reference scenario that contains no constraining GHG reduction targets. It has to meet and follow macroeconomic assumptions published by the Canada Energy Regulator, by Statistics Canada and others. So for GDP, population, oil and gas export prices, and many others. The scenario, as well as the net zero ones, includes all GHG reduction and energy policies already in place at the national and provincial level, in addition to two that we thought were particularly important, even though they're not fully in place yet. So that's the clean electricity regulations and the zero emission vehicle sales mandate for 100% zero emission vehicles sold by 2035. So I'll discuss some of these in the results in just a bit. So then the main net zero scenario is NZ50. So it imposes basically two federal targets. So the minus 40% by 2030, and then net zero by 2050, and then NZ50 PS, which you'll see on the chart, is basically a sensitivity analysis for the cost projected for nuclear SMRs, which are higher in this particular scenario. So I'll get to that topic when we talk about electricity in just a little bit. And so the results for total emissions that you see on the right, by design, NZ50 reaches zero net, I should say, by 2050, and then REF doesn't. It does go down, and I'll delve into that as well, but diverges pretty quickly from the NZ50 trajectory. Okay, so let me start the overview. I'll do GHGs and then energy consumption sector by sector, and then leading to some key takeaways towards the end. So for those of you less familiar, perhaps with this kind of graphic presentation, all the charts are similar. You'll find quite a few of them in the actual report, but also in the presentation. So it's always the same principle. You have the reference year, which is 2021, and then you have groups of bars for each of the scenarios. Or once per decade, so 2030, 2040, 2050, and 2060. So each of the bars represent the reference scenario and then the two net zero ones that I just described, right? So if you look at this chart, so this is total emissions by sector across the country, a few things that stand out. So the current measures put in place, and like I said, some of the announced ones do lead to a reduction of emissions. But short of the 2030 target of minus 40%. There is a rapidly expanding gap between the net zero scenarios and the reference one. And overall, it shows us that it is possible to get to net zero by 2050, but it requires a very rapid move away from the current path. And to be perhaps a bit more specific, if we are to reach net zero at reasonable cost, it appears necessary to that all sectors in all provinces and territories get into a deep decarbonization as quickly as possible. So another thing I want to mention on this high-level chart is what you see in the red circle, which is remaining emissions. So with current technologies, including those in development, there's a significant quantity of emissions that cannot be eliminated or captured, either because of technical constraints. So for instance, non-energy related emissions from agriculture don't go away, at least not in their entirety, industrial process emissions as well, or because of cost in some subsectors of transport, for instance. Some emissions remain as well. So it means that these emissions must be either captured, so in some cases it's possible for industrial process emissions, for instance, or be compensated by removing GHGs from the atmosphere, so either through direct air capture technologies or through negative emissions technologies, for instance, when you use bioenergy coupled with carbon capture. So I'll discuss this particular topic on a distinct chart in just a few minutes. But first, let me move into the transformation of energy consumption. So demand goes down, the total demand that is for energy goes down in the net zero scenario. So you see the bars for NZ50 going down in 2030, 2040, 2050. So this is despite population growth and even without loss in energy services. So among the assumptions and the constraints in those scenarios, there is a meeting of demands for different sectors that needs to be respected, and therefore the model will not necessarily decide to eliminate 50% of transport demand just because it leads to reductions. So we take a conservative stance here and maintain the demand projections. So because of productivity gains, which are pretty substantial in the delivery of services, including first and foremost from electrification, but also other measures, you have an overall demand that goes down. There is also, however, an important rebound after 2050. If you look at the net zero scenario in the groups of bars on the right, you see that it goes up pretty quickly after 2050. And that's because to meet the net zero constraint, basically all the solutions available at reasonable costs are taken. And then after that, it becomes more difficult to realize further emission cuts, which means that it's more costly, which means that it also leads to more energy consumption as a result. It's something to keep in mind as we move into sectors. So I'll start with transport, one of the two main sources of emissions across the country. So I'll show you two charts here, perhaps for the overview. One is energy consumption in transport. So the chart you have here is by energy source. So, gasoline, diesel, natural gas, and so on. So one thing to notice is that the ZEV mandate leads to the electrification of light-duty vehicles. So that is in the reference scenario. And then there is limited decarbonization in the reference scenario outside of this segment. So this is where the departure is more in the 2030s. NZ50 will start decarbonizing other sectors, including heavy road transport, where there's a much more or a much deeper penetration of electricity, but also some hydrogen later on. There's also a full electrification of rail, and so on and so on. One thing to mention here is that in some subsectors, there are choices that lie ahead, where we see in the results an eclectic mix of technologies to decarbonize. And NZ50, for instance, I'll take heavy road transport again. There's some hydrogen, some battery electric vehicles, some catenary, and so on. So in practice, it's unlikely that all of these infrastructure will be built in concurrence. Instead, very likely political choices will pick an orientation at some point, and it may vary across regions. There are also constraints in broader regions, or for instance, for heavy road transport, you have a lot of long haul, which means that it's not just one province at a time, but it's several provinces and some US states and so on. So there's a need for standardization that may lead to very different results, of course. But indeed, in the absence of specific measures like the ZEV mandate, we don't project any substantial reductions beyond some electrification of medium-duty vehicles. Second chart I wanted to show for transport is the emissions by subsector. So you have road transport, rail, off-road, marine, and air. So two things to notice here. One is the evolution of scenarios, including the reference one, which shows a growing importance of some segments, a relative importance, that is. So if you look at the green bar or light green bars on the chart, so they go down. So this is road transport. So that's the result of electrification mostly. But then you see also the gray bars, which is off-road transport. So this is on-site transport for industry, commercial activities, agriculture, and so on. Over time, this becomes the main source of emissions for transport, even in the reference scenario. Perhaps even more important in the net zero scenarios in relative terms, which tells us certainly that there needs to be a bit more attention put on that sector. So it's a very eclectic set of services provided. So it's a little bit difficult to put in place one-size-fits-all measures, but in any case, more attention should be put here. The second thing I wanted to point out is the high cost of decarbonization options for marine and air, which show up in the results, as there are relatively few changes, even in net zero scenarios. Now, the second main source of emissions across the country, energy production. So just to state right off the bat that there is a floor imposed on oil and gas production, especially which has an impact, especially on the shorter term. So production does go down, and eventually on the medium term goes down pretty drastically for oil production. So there's all sorts of questions, as I'm sure you're aware, on this particular topic in the Canadian context, the geographic concentration of the industry, the question of employment, the loss in $200 billion of yearly export revenues. All of that requires very special attention on how to develop a plan forward. But I'm mostly going to mention here the fact that in any case, and just to inform that debate, not reducing oil and gas production as extensively as in the net zero scenarios means reducing elsewhere to meet net zero. And most of that is done at much higher cost, right? So in the end, that needs to be taken into account as well. So we have a longer discussion in the report on this difficult issue as well. In terms of natural gas and uranium production, just to mention that most of the evolution in the net zero scenarios in particular are driven by domestic demand. So, the share of natural gas that remains for net zero scenarios, and then the increased use of uranium for nuclear electricity generation, especially in the net zero scenarios again. So as we get better numbers for export market projections, of course, some of this may change slightly or perhaps more substantially, but in any case, that's the main driver for the changes that you'll see on this particular chart. Now, electricity generation. There's a lot to be said here. I'm still going to stay at a high level. So electricity demand expands dramatically, to put it as clearly as possible in all the net zero scenarios. Also, the reference scenario, which is an important point. But in net zero scenarios, at the national level, it's more than doubling of electricity generation. And most of that comes from more wind, solar, and a lot more nuclear SMRs, as I mentioned quickly earlier. So, of course, in the scenario here, the main one at least, we suppose that for other technologies, SMRs will be available at the cost planned. But if that's the case, indeed, they show up pretty strongly, as you see in these results. So we did do a sensitivity analysis on this because of the many uncertainties that still exist. So some provinces have delved into developing SMRs much more strongly, but they have yet to be in function, right? So in the net zero PS scenario, we have higher cost projections for SMRs. So the result is indeed a less strong showing, which has repercussions elsewhere in the capacity mix, so more wind and more solar in particular. But perhaps something interesting to chew on here is that regardless of the specifics of SMR deployment per se, the comparison of the results between NZ50 and NZ50PS allows for a reflection over choices to make for additional baseload deployment of any form, actually. So in other words, we can see NZ50PS's results as a future which compares with NZ50 by stating, what if less baseload is available at reasonable cost for all sorts of reasons, right? Higher or ballooning costs for large-scale projects, social acceptability problem, some provinces that may decide to refuse the nuclear option completely, and so on and so on, right? So the rest of the evolution of the mix and the extent of electrification as a preferred decarbonization pathway becomes visible when you draw these comparisons. So I'll return also to deployment challenges in the takeaway section in a few minutes. The industry sector, so this is industry outside of energy production. I said oil and gas, but energy production. So I can't do justice to the complexity of the sector in under 2 minutes, but perhaps a few things to mention at a high level. In the case of energy consumption, which you have at the top, there's already a pretty diversified energy mix in industry, a lot of electricity, a lot of biomass, and so on. And the mix evolves relatively slowly in net zero scenarios, which really highlights the barriers to fully transform that consumption. But also, perhaps more importantly, the differences across the subsectors are significant. The challenges are not exactly the same. And indeed, the difference between emissions associated with energy combustion versus industrial processes, which is split about half and half at the moment, becomes much more important along the time horizon. So even in net zero scenarios, as you see in the bottom chart, which is emissions for the industrial processes part. So net zero scenarios, Combustion of energy is completely decarbonized in industry, but emissions from processes remain at a little over half of what they are today, right? So significant reductions, certainly, but also a pretty big chunk of what remains in terms of net emissions at the end of the horizon. And finally, the building sector. So like many others and like our own results in the past, there's some stabilization of the evolution here. So for most of the decarbonization pathway, it goes through, first and foremost, electrification. But there are many barriers here. So the technology exists, the cost is relatively low, but just the sheer number of buildings to transform has put some restrictions on the pace of this transformation, which is also happening in the reference scenario, by the way, but at a slower pace than what's needed in the net zero scenario, as you see in the results. Among the challenges here, beyond labor and logistical issues and, planning renovations and so on, the pressure it creates on winter peak and electricity demand is a pretty urgent matter to plan for. Some provinces are already facing that problem. Provinces that are more advanced in their electrification of buildings, but it's an issue that's going to come up for provinces with a much higher share of natural gas for space heating at the moment, which will need substantial additional capacity, but also management of the winter peak much more closely. All right, so the question of capturing emissions. So I wanted to put this in context here. It's a little bit misleading, actually, on the first chart I showed you, where you see a little over 100 megatons of net emissions remaining, because on that chart, on the previous chart, it's net emissions by sector, which doesn't show you the full extent of capture and storage. So reaching and maintaining net zero requires in NZ50 an annual capture rate of 172 megatons in 2050, right? So about 2/3 of that is negative emissions. The other third is CCS applications in industry outside of oil and gas production. So this becomes important even more after 2050, because as I said earlier, due to the lack of further reduction techniques that are economically viable, the requirement for more capture becomes even more important past 2050. So of course, in the analysis we present, we take a mostly technological approach, which means that we have to treat this result with very special attention. It is in fact a giant caveat that suggests that yes, reaching net zero is possible given current knowledge on technologies and projections and so on. But it also tells us that given this result here, the very large challenges that it creates, the net zero scenario, that is our gross underestimation of the true needs. On the one hand, you have an evolution of the scenarios which presents an optimal allocation of resources across the economy, which of course in practice is difficult to realize, and 172 megatons of capture and storage, right? So to be clear, we're starting from around zero now. So that would mean around 8 megatons of negative emissions capacity built every year from now to 2050. So with the obvious questions that it raises, which I'll get back to in the conclusion. Quick word on hydrogen and bioenergy. So here you have consumption at the top for hydrogen and production at the bottom. Production is put in terms of the technology used. So consumption is much smaller in REF, but it grows. Mostly driven by exports, though, whereas in NZ50, hydrogen appears as one of the tools to decarbonize some hard-to-abate sectors where electrification is more difficult or extremely costly, for instance. That being said, of course, it's difficult to project with any level of precision the adoption of hydrogen. There's, at the very least, the issue of developing infrastructure, a lot of it from scratch, in some regions of the country, which means that the early choices will make the second ones and the third ones codependent, and therefore it could result in various pathways that are hard to predict with certainty. But certainly that points to the need for very careful planification, or planning, I should say, of where hydrogen can be used to have the largest impact in terms of decarbonization as opposed to just expanding hydrogen production. Also, something to notice on the bottom chart is that the technologies used or the way to produce hydrogen differ a lot across scenarios. So in the reference scenario, the projection shows no difference from what's being done today. So gray hydrogen in the net zero scenario is a completely decarbonized production, or almost fully decarbonized production with blue hydrogen, but green hydrogen as well as cost decreased on the longer term. You may notice that electrolysis doesn't show up pretty strongly here, but that's largely linked to the negative emissions associated with the BECCS process, right? So of course, if GHG accounting for negative emissions changes, or if we consider it differently, it may change these results, but we'll see in the future. Bioenergy triples in net zero scenarios by 2030. Then it reaches more or less a ceiling due to the resource availability, due to cost, but also due to the remaining emissions associated with biofuels. So it helps put a dent in emissions first, but then eventually the remaining emissions catches up on the scenario. So most of the expanded use of bioenergy is used for negative emissions applications in these results. So that's agricultural residues, across the provinces, forest residues where they're available depending on the province. And a lot of that is used to produce syngas with the biochar associated product, or the longer term, mostly BECCS hydrogen and electricity production, a little bit of heat in industry as well. So two more words before discussing the key or some of the key takeaways. One thing is about the 2030 target, right? So we have this little table, sector by sector expected emission reductions in the reference scenario, and then the NZ51 in the concluding chapter. So the main emission reductions expected for 2030 are from oil and gas production, but especially buildings and electricity generation. However, we're in mid-2024 now, so the much faster pace required by the NZ50 results, which by design, again, has to meet the 40% reduction target, tells us that meeting the 2030 target is at this point almost structurally impossible. It's going to be very hard to do that, and it's not because there are no further reductions expected, but some of the very strong measures that were put in place recently, or are about to be, the ZEV mandate, the clean electricity regulations, they're all going to have most of their impact past 2030. So they are, of course, having a pretty important impact, but it's not showing up for the 2030 target. And just to clarify, we project a 14% reduction here from 2005 levels. So we don't use a projection for LULUCF and for nature-based solutions, I should say, and from carbon credit imports from the California market, as Environment and Climate Change Canada does. So if we take their number, which is 45 megatons contribution for 2030, we would reach a 20% projection. So still very short of the 40% target that is legislated at the moment. Another comparison to make is between this edition and the previous one. So it's always interesting to see how the results change and how the projections evolve. Some of the main differences, one is a good one. So the reference scenario shows reductions, not increases like the last time around. For GHG emissions. So that's the impact of many measures put in place, the ZEV mandate, the CER, the Clean Fuel Standard, and many others. So that's good news with the caveat that it's not enough, as I mentioned earlier, but nonetheless, certainly an important change. Also, the costs of decarbonizing are much less than the projections for net zero in 2021. So this is because technological developments are rapid. They provide solutions at lower cost, even over the 3-year period. But also importantly, perhaps they help reduce uncertainties about short to medium term projections, right? As technologies develop, we get more certainty on cost projections and rate of adoption and so on and so on. So that contributes as well. In terms of similarities, one by one, but the main ones that I think are here, the dramatic expansion of electricity, similar as in 2021, including in the reference scenario. The reduction in crude oil production to mitigate cost, sorry for the typo here, to mitigate cost at the national level for the decarbonization pathway, with all the caveats for this particular topic I mentioned earlier. And then the magnitude of the needs for emissions compensation given current knowledge. So here we have biochar that was added as a technological option, which wasn't there in 2021, but overall the total amount of emissions neutralization compensation is about the same. So some of the key takeaways, I strongly invite you, of course, to look into chapter 6 and longer presentation of these, but I'm going to do my best here to present the main ones. One is that net zero requires making choices, as we've said before, that are already compatible with the long-term goal, regardless of the short-term target and any benefits in terms of short-term reductions, right? So we need additional measures and roadmaps to enable the net zero pathway, including from provinces where less or fewer structuring measures were put in place over the past few years compared to the federal level. Also among this planning or within this planning, there's no time really for dead-end solutions that require the building of infrastructure that will need to be removed in 10, 15, 20 years. Of course, there's a question of cost, there's a question of path dependency, so it's difficult to unconstruct infrastructure, so something to keep in mind, but also because the challenges and the transformations that are required are already very significant. So adding a new one to do 2 transformations in a row is just not possible here. Another takeaway is regarding the challenges that are associated with the very significant infrastructure gap. And so deployment plans developed rapidly, integrated resource plans in particular. So some provinces have been getting into this recently. That's great news. So more of this is needed, ideally with planning that is reviewed very frequently. Then the expansion of electricity's role. So I'm not going to get into the discussion of construction and so on. Of course, given the size of what we're talking about, it's very significant. But I'm going to mention as well that it's not simply a challenge in terms of construction. It also requires a complete rethinking of how to support an economy, mainly with electricity, because that's what we're talking about for 2050, as opposed to the traditional energy mix used in the past. So more resilience needed because more services will be provided by electricity, different ways of developing the networks, also developing for regional industrial development, developing the grid ahead of the actual construction of industries. So that's also a rupture from what has been done in the past and to a large extent. And also, as I mentioned, for heavy road transport, for instance, there are some sectors where competing technologies require political choices so that we don't overbuild unnecessarily infrastructure for whatever reason. And last one I'm going to mention is the need for roadmaps to reduce uncertainties and unknowns. So 4 ways that this is illustrated in the discussion we have in the report. First, there are very clearly understudied sectors. So there could be relatively low-hanging fruits in there. But in any case, knowing a little bit more about what needs to be done at a more refined level will be certainly a good way to move forward. So I mentioned off-road transport. There are many industrial subsectors that suffer from a lack of attention as well. Then roadmaps needed for sectors where few reductions are expected. So industrial processes again come to mind, but also agriculture. So a little bit more clarification of how to move forward despite the very large uncertainties that are facing these sectors today. Third point I wanted to mention is a better assessment of the role of biomass in decarbonization pathways. So in this report, of course, we talk about biomass from the bioenergy perspective, and that's part of it, but there are also other strategies linked to biomass and LULUCF more generally, perhaps, So that needs to be clarified. So as Normand mentioned, we have another project ongoing at the IET on how to determine a grid to prioritize different development of or contributions, I should say, of biomass to these pathways. And last one I'm going to mention is the urgent exploration and planning needed for the deployment of negative emissions. It's not because we're going to need them to the extent that I presented earlier. That's not really the point. The point is that we're talking about a very large scale contribution with almost none of it existing today. So clarifying what the true realistic potential of each of these technologies is in practice is very urgent. All that being said, though, most of the attention needs to remain on innovation for reducing emissions rather than compensating them for many reasons, most of which are covered in the concluding sections of the report. So building on these results and some of the issues, the challenges they raise, especially the urgent ones, we have several new projects in development for part 3 of the Outlook in the fall. So stay tuned, and I will be happy to present them to you in a few months.
Thank you very much, Simon. Before letting Louis handle the questions period, I just would like to add maybe a few things. This is based on optimization modeling, and one of the things that comes out is in electricity, for example, where you see that this demand is maybe somewhat lower. The projected production of electricity is somewhat lower than in other models. It's really when you optimize everything, and this model supposes that you use the best technology everywhere. So this is really kind of the floor demand for electricity. So it is really likely that as we attract industry from outside that will be energy intensive, as other new technologies or new industries develop that we cannot predict, we cannot project, there will be a demand for more electricity. So that's, I think it's an important point that is not always put forward. And as Simon was saying, there's much more information in the 140 some pages of this report. So have a look at the paper. So I'll let Louis now for the question period.
Thank you, Normand, for those additional comments. There's one question I can answer right now. If everything that we are presenting today will be made available on our website, including the recording of that webinar. So one first question on the SMRs. Can you talk a bit more on why SMRs are showing so prominently, and is it only based on cost consideration, or is there any other considerations?
Well, there's one other consideration. It's mostly cost, but the cost, perhaps a little caveat. I forget if I mentioned it earlier, but there is a waste heat recovery technology attached to it, and that's applied at least in some of the deployment in the results. And so it reduces the overall cost on an energy basis. So that's part of the reason why it shows up strongly in some provinces, but nonetheless, it shows up even in provinces where that economy isn't there, that saving isn't there. I don't know, Kathleen, if you want to add something to that, but.
No, that's okay. I just also provide a response in written.
Yeah, thank you.
I mean, one of the easy reason why we see SMR in our result and not much in other work is that we find out that other works just don't include SMRs most of the time, or they have very pessimistic assumptions on the cost evolution, because it's true that there's not much available. So I think we should just not exclude. Our position is to not exclude any options, and then the decision making can just deal with that social acceptability issue after.
Thank you, Kathleen. Two questions here. Is the base year is 2021, but is it aligned with the National Inventory Report of 2023?
Yes.
Yes, thank you. And was the oil and gas emission cap model in this report under the net zero 2050 scenario?
No.
That's a good question. I don't remember if we have included or not, but I don't think so.
It's not actually. We had that discussion earlier, but it's not. We do touch on that topic in the conclusion as well, just to clarify that we're not expecting a reduction from that. So of course it could change depending on the form of the cap.
Dead-end solutions, are we talking about oil and gas infrastructure?
Partly. I think that the generic definition is, that in the sense that we use the expression at least, is a solution that may help on the shorter term for various objectives. It could be emission reductions, partial emissions reduction, partial decarbonization. It could also be something else, development or whatever else. But it leads to a construction of infrastructure that needs to be removed or retransformed on the 2050 horizon. That's the short definition. So that could be, for instance, natural gas used in heavy transport, which don't show up in the results for 2050 at all. So if you choose to deploy it, then you have to think removing some of the infrastructure you've put in place. So removing infrastructure happens rarely. Again, so because it's costly and because for various reasons, it's just difficult to remove, various social, political reasons as well. So something to keep in mind for the thinking about the dead-end solutions as well.
And you could even include, for example, electric baseboards, which are much more electricity intensive than heat pumps. And if you have to replace this in terms of how you reorganize your heating system in buildings, is very costly. So this kind of raises the cost of the energy transition.
Here, a question on are there significant differences in capital cost assumptions for various decarbonization technologies between the reference and the net zero scenarios?
I can answer. Kathleen, do you want to answer, or?
So who wants to start? Maybe Simon, go with that.
Yeah. Or go ahead, Kathleen.
There's no difference in cost assumption between scenarios, but the fact that carbon price will not be the same.
So we're losing Kathleen, so maybe I will answer. Essentially, we put the same carbon price at 200 to 2030, and then the difference in adoption is because of the constraints. So we're constraining on emissions, and this constraint in emission will then find the optimal solution given the amount of emissions is allowed. So in the reference scenario, there's no constraint on how much emissions there are. So the only thing that are reducing emissions are regulatory the forces plus the current carbon price. When we do the other scenarios, we impose a total amount of emissions, and therefore technologies that don't emerge without a bit of a push somehow will emerge. And that's what you will see in the report. We have a cost function, the marginal cost function as a function of a CO2 remove. And that really tells you how the new technologies or how these choices are made to reflect the imposition of this constraint on global emissions.
Thank you, Normand. While we're talking about the cost assumptions, what about the learning rates or the declines in technology cost? What are the assumptions throughout the projection period?
I don't know if Kathleen's back, but maybe I can answer this one. So all the cost assumptions come from a review of the literature. Typically, if there's more than one in a wide range, it's a conservative midpoint estimate, basically. Not too optimistic, not too pessimistic for both the cost projections and their decline basically over time.
And it's important when we compare our three energy outlook, we see that we tend to be more conservative than what's happening on the ground for some of these technologies. And that's why the cost of this transition keeps going down, for example, between the three sequences of outlook we published. plus, of course, the arrival of new technologies that were not even included because they were too far-fetched a few years ago.
Kathleen, you're back with us. Do you want to add something to that?
No, that's it.
Thank you. One question here about the 2030 electricity generation increase that seems to be almost the same as 2021. So can you explain, is it, maybe the question is not, I'm not sure I understand the question clearly. Is it compared to our 2021 energy outlook, or on the 2021 reference data from the scenario?
Yeah, maybe you can you move back to the slide, Simon?
So the comparison here?
No, if you go to the slide on electricity generation.
Oh, sorry. Yeah. Right here.
Yeah.
It's a 5% increase by 2030, more or less. So between 5 and 7%, depending on the scenario. And then expands more drastically after that. So it's electrification on the short term, but to a level where the gain in productivity keeps it in control. But after that, it drifts away pretty quickly or expands very quickly.
And of course, this does not include any new industry that was not in the industrial, part of the industrial fabric of 2021. So that's so all the new mega factories, for example, that will be needing more electricity are not included in this.
One more question here. Does electricity demand account for hydrogen electrolysis?
Well, yes, it does, but in the results, there's not that much electrolysis for producing hydrogen. I think I put it earlier, but you see it on the bottom chart here. So most of the hydrogen is produced in other ways, largely due to the side benefit of negative emissions. So that's the reason you see it here. So no electricity showing up that, or at least not that much for that particular part.
Thank you. One other question on the how these projections take into account changes in climate or risk and costs associated with continuing with business as usual.
The short answer is that they don't. And because of the nature of the modeling, we take the conservative assumption that all demand projections are realized. We also take projection estimates for the availability of different resources. So for biomass, for instance, that's a pretty big question mark because of the factor that the question mentions. So of course, there are different ways of reading these results. I strongly encourage you to look into them on your own. But certainly the question of how to understand the needs for the future is really there. So we try to give a reference point for the discussion. And like Normand said earlier, it is an underestimation because of the optimization process, but also because of the conservative hypotheses on industrial development, for instance. So no new industries and so on. Right? So it gives you a sense of the magnitude. But of course, if you add on to that some hypotheses over changes in biomass availability, then it leads to other resources. In the 2021 edition, we did a sensitivity analysis for that in particular, but hopefully we'll be able to do it again in a few months.
But we do account for temperature, the effect of the different temperature projection on demand for space heating, space cooling. So there's a part of the future climate change that we integrate in the model.
Thank you. So how drastically are these data impacted if the carbon tax is eliminated entirely?
The impact is huge. Yeah, I mean, we will have less. There are some trends that are there to stay, but there's a lot that is impacted by the carbon tax, including in the reference case and in the, of course, the net zero. If you remove all price signal or constraint signal, I mean, you don't reach net zero. So that's a completely different kind of story.
But nevertheless, regulations play a big role, because when you look at the reductions between 2030 and 2040, the carbon price is kept constant. And what is really driving the reduction of emissions in the reference scenario is really the regulation on clean electricity and the ZEV mandate. So you can have regulations that have huge impact, and we see it clearly when we look at this 10-year period over which the two regulations really deploy.
How is reliability of the electricity system assured or considered within the model, assuming a reserve margin, or the representative days and weeks that are in the model?
Yeah, all that. We have reserve margin, we have representative days, week. We also sometimes use peaks to average ratio when we are not able to capture the peak adequately, because doing an average on days is not having it's not the same thing as having the full hour. So we have a bunch of strategies to deal with that. But of course, it will never be as precise on the electricity planning side than with an electricity model, or like with our need and power model, for instance.
Thank you. Can you speak to potential international assumptions used in the model and why they are chosen, or how they impact the net zero scenarios?
International assumptions, we use like evolution of oil and gas price on the international market. So we calibrate to CER, the reference at their reference, and our net zero is taking into account their assumption of their international net zero scenario of CER. So quite much lower prices on the national market, and it affects the result on oil and gas, of course. And we also look at like the export demand for these products, oil and gas, using the CER. So it's quite different assumptions between the two scenario, reference and zero, regarding this in general. The rest is yeah, there's no other main assumption that drives the result that this one on the international side.
I mean, although it's not exactly linked to these questions, I mean, one of the interesting aspects of our modeling is also that we go to 2060. So it is possible to also capture if 30 years ahead, but the fact that the economy and the electricity and the energy system continues to transform even once you're at net zero. And so it's not 2050 is not the end of the world. There are things happening, and even when you're at net zero, there are structural changes that are occurring in the energy sector that at least are projected in these models.
Thank you, Normand. So we're coming at the end of the hour. We have answered all of the questions that were posted in the Q&A section. If you do have more questions, please contact us. We'll be happy to answer them. If you want, Simon, Normand, if you want to make one final statement before we end this webinar.
I think I encourage you to read really the report, to have a look. The report will be online soon, by today, all the documents, and make sure, don't hesitate to contact us if you have further questions or interest.
Yeah, that's what I was going to say as well. Don't hesitate to reach out, even if it's in a little while. We'll be happy to look into your questions.
Well, thank you. Well, thank you very much, everyone. Thank you for joining us, and stay tuned for more to come in the coming months. Thank you very much.
Thank you.
Thank you.